Okay, so let's go ahead and work this, this constant acceleration example. And in this problem, we have a car that is accelerating up some freeway ramp. And we're told that it has an initial velocity of 10 meters per second. The ramp is 200 meters long. And the car accelerates, I didn't write that down, the car accelerates at 2 meters per second squared. Okay? So what we're asked to find in this problem is how long does it take the car to get to the end of that ramp? Okay? So we have some initial speed. That car accelerates up the ramp. And we want to know how long it took the car to get to the end of that 200-meter ramp. And as usual, it's really useful to draw a figure. And this is sort of a messy one, but nonetheless, what I've drawn here, I've drawn our initial position, I've drawn the final position, and I've drawn the other relevant stuff onto the figure. A 200-meter long distance between the final position and initial position. I have the initial velocity drawn on here. And I've just indicated the acceleration somewhere on the figure. Okay, so once we have our figure in place, the next step to solve a problem like this is to write down what we know. Okay, so let's go ahead and write down what we know. Okay, well, we know what the initial velocity is. Okay, it's written right up here. We know what the acceleration is. Okay. And we know what the displacement is. We know what the final position minus the initial position is. Okay. The final position minus the initial position is the displacement. And we know that's the length of the ramp, 200 meters. So I'm just going to write that in here. So it's 200 meters. Okay, so we know those things. So we don't know, or what we want to know the time it took the car to do this. Okay, so that's the elapsed time or the final time. I believe most of the equations we have it as delta t. Okay, so that's what we want. We know these things. So at this stage, it's kind of hard to see that in the glare right now. At this stage, we want to go through our equations and try to find the equation that best fits this set of variables. Okay, so we have that list of 3 equations we just went over in the lecture. And we want to use the equation that best fits this information here. And the equation that best works for that set of variables there is this one. Okay? That's the equation that best fits this set of variables. We have the final and initial position. That's up over here. We have the initial velocity. Okay, we know that. The time. That's what we want to find. So I should say this is, we're going to just make it all final time here, just to make it a little bit easier. Okay, we have the acceleration, that's one of our givens, and then there's our time appearing again. Okay, so let's go ahead and plug the stuff in that we know. Okay, well, if we bring the x, if we subtract both sides by this, we get x final minus x initial on this side, and that's what we were given, which is 200 meters. So we get 200, that equals our initial velocity, which is 10, times the time, plus 1/2 times the acceleration. The acceleration was 2, so 1/2 times 2 is 1. So plus 1 times t squared. Okay, now if we subtract 200 from both sides, we get something that looks fairly familiar. So let's subtract 200 from both sides. If we subtract 200 from both sides, 200 minus 200 is 0, so we get 0 over here. And we get minus 200 over here. Okay, so we now have a quadratic equation. And we need to go to the quadratic formula to actually solve this. And so remember, the quadratic formula is on the slide that has this problem. And I'm not going to write it out again. But nonetheless, it allows us to solve for the time. And the quadratic formula tells us that the solution to this is negative b plus or minus the square root of b squared minus 4ac. Okay? So a is 1 for the quadratic formula, b is 10, and c is minus 200. Okay? So using the quadratic formula then, the time is negative b, so b is 10, so we get negative 10 plus or minus the square root of b squared, so that's 10 squared, which is 100, minus 4 times AC. A is 1, C is minus 200. So 4 times 1 times minus 200 is negative 800. So we get minus negative 800. And that's divided by 2 times A. A is 1, so 2 times 1 is 2. Okay, so we're almost there now. Negative 10 divided by 2 is minus 5. Okay, plus or minus this divided by 2. So let's look at this here. We have 100 minus minus 800. Minus minus becomes a plus. So 100 plus 800 is 900. And if you take the square root of 900, you get 30. Just do that on your calculator. The square root of 900 is 30. So we're left with 30 here divided by 2. 30 divided by 2 is 15. Okay? So let's go ahead and erase this other stuff up here, just so we create some space. Need that too. Okay? So we're told that the time is negative 5 plus or minus 15. So time then, the solution, we get two solutions actually, one corresponding to the plus, one corresponding to the minus. So negative 5 plus 15 is 10. So here's our two solutions. The first one is 10 seconds. The other one is the minus. So negative 5 minus 15 is minus 20 seconds. Okay, that might seem kind of confusing at first. We have two solutions. But one of them is what we would call an unphysical solution. It doesn't make any sense for the problem. Okay? It doesn't make sense to have a negative time because this event happened after this event. Okay? A negative answer implies it happened before. So this is an unphysical solution and we can just eliminate it. Okay? So the solution to this problem is 10 seconds. Okay? It took 10 seconds for the train to accelerate up the ramp with this initial speed and that acceleration.